So back to that first point on the reduced energy consumption. The main reason they save so much electricity or power is because of this, what's known as the fan or the pump law, pump affinity law. So this is the equation here, and so this is when there's variable torque loads. So things like centrifugal and axial pumps, fans, blowers, mixers, agitators, all these types of equipment have what's known as a variable torque load. So this is not requiring the same force or pressure all the time. So you can slow the motor down, reduce the torque, and reduce the pressure. So this equation here really, so we have like two situations. So we have like case 1 and case 2. So if you slow the shaft speed down by half, so you reducing by 50% that required shaft speed, you then effectively have 2 to the power of 3, which is 8 reduction in the power required in that second situation. So you're saying for a 50% reduction in speed, you get you require like 1/8 or 12.5% of the power to achieve that. And there's also a quarter reduction in the torque. So that's really what's driving the energy savings. And I'll kind of run through some examples and explain that a bit further as we go. I'll just mention also that, so this is for the variable torque loads. This equation and the calculations don't necessarily apply for constant torque loads, which is when you might need to slow the shaft speed, but you still need that same level of force, or rotating force or torque, and so it's proportional to the power. So they're things like if you've got a conveyor motors, reciprocating pumps, or compressors. So there's often still significant savings there just because that improved control when compared to the typical techniques for that reduced speed, or but it doesn't have that kind of cubed root or the power of 3 benefits. So we'll see. So this graph here on the left really just shows that relationship there between the flow, the pressure, or look at that as force as well, and the power. So you can see there's the relative speed or the wheel velocity down that x-axis. As that increases, the pressure and the power requirements maybe increase dramatically. Based on that same relationship I just showed on the previous slide. And there's some calculations on the right there just kind of showing that another way. So if you're just running 100%, the power reduction is 0, but even a 10% reduction in speed, you see up to a 27% power reduction. And then that just kind of continues down. So to that example I gave before, so 50% reduction, just say a 12.5% power reduction equivalent. And then I'll just run through like a worked example of that, so say, just to drive that home a little bit. So we've got a 100 kilowatt pump, and we install the VSD and then reduce the flow speed by 10%. So in that initial case, we've got so it's running 100%, so it's using 100 kilowatts. There'll be some losses and other factors in there, but just generally speaking, say 100 kilowatts, and the speed is 1 or 100%. Then we install the VSD, we reduce our N2, our speed down to 90%, so a 10% reduction. And then you can see there that calculation through to determine what that second power requirement is going to be. So it's the initial power divided by that ratio of the initial to the final power cubed. That's 100 divided by 1 on 0.9 to the power of 3. And yeah, you can see there that second power requirement is 73 kilowatts. So for a 10% reduction, we've saved 20% of our power requirement, which is pretty considerable. You're probably wondering how much they cost, and they do vary. It depends on the size of the VSD. The costs increase as you go to a larger motor size, unsurprisingly, but also the cost per kilowatt comes down. So I've just got 3 example cases here, just from some recent ones we've looked at. And so that for 1 kilowatt, which is right at the end, at the bottom end of the scale of what is you can consider for a VSD, they do get smaller. So it's technically possible, but the economics really start to struggle at that lower end. So you see there like $1,000 for a VSD plus an install, so you're looking at $1,250 for the total cost, and then as you step up to 15 kilowatts, the cost goes up, but the cost per watt's a lot lower. Cost per kilowatt is much lower, and yeah, then the total cost as well is there. And then 75 kilowatts, which is getting to the they go up to above 500 kilowatts VSD controls, but yeah, 75 kilowatts is pretty typical. You know, you'd see on large drives or compressors around about $10,000 for the unit. So yeah, plus installation, yeah, looking around about $14,000–15,000. And so that's, yeah, a bit of sets the scene a bit. And so the other thing to worry about or consider is whether it's right for your site, your situation. And they're quite versatile VSDs. There's not many AC induction motors they're not suitable for. There's just a few key considerations there. I mean, the main one outside of the technical considerations is the economics of it, which I'll get to in a second. But just some considerations are available space. If you're quite restricted on where on floor plate for your site, they do take up a little bit of room, so making sure that there's room for them to be installed. Another thing to consider there with the available space is the temperature. Various variable speed drives in really hot conditions can sometimes struggle performance-wise. So if there's only that roof space, or you're dealing with temperatures above 40 degrees, that might be something to look into a bit further before you go ahead with that. There's somewhere else to position it to. The electrical system at site is something else also to look into, and it's mainly around whether there's power factor correction on your site. So variable speed drives effectively do power factor correction for the motor or whatever it's been installed on, just through that electronic control process. But if there's also so that's, yeah, something to watch out for. And also whether there's the variable speed drive is controlling multiple motors. Yeah, that's something to look into, just to make sure that you want the variable speed drive size so that the maximum current through the motor is going to be within the working limit of the variable speed drive. So if you've got multiple units on the same variable speed drive, just make sure that the sum of those peak currents is still under that limit. So they're kind of just some of the physical or technical considerations. The economics is probably, once you kind of it's suitable for your situation, then it's time to look at whether it's financially viable, and that's really relative to the other alternatives. And I suppose the first one there is just to do nothing. So that's whether the variable speed drive makes sense on its own, or you can do some quick calculations and looks like the costs are too high or the payback isn't there, then leaving it may be an option, or controlling it manually yourself, whether there's staging you can engage on the motor, or just manual controls, just conserving energy, switching it off when it's not required, things like that might be another alternative. If the load isn't really that variable, then maybe just installing a high efficiency motor, which is a particular type of motor that's labelled high efficiency, like accredited as a high efficiency motor. Typically have a 3 or 4% efficiency improvement over typical motors, so that may be more cost-effective option for you. And then kind of in line with that is whether right sizing of that motor is an option for you. Often motors will be oversized, and planning on plan expansions when things are installed, or just wanting to make sure you've got enough capacity. Oversizing motors is fairly common, and can result in like the motor using too much or unnecessary power use for that bit of kit. So they're the main considerations for the economics of it. I'll kind of run through a worked example now, just to explain how we work out whether that's looking like it'll be financially viable. So before I do, I'll just run through. So Kartik and I were recently down at Forager Foods, down a fruit snack producer down in Tasmania. So they're a site there. They've got a range of motors and pumps on site. So they've got air compressors, refrigeration compressors, cool rooms. Their main energy using equipment, however, is their freeze dryers, which have vacuum pumps which create a vacuum within those freeze dryers. So you can see there that's kind of the chamber opened up in that picture there. The vacuum pumps to create a vacuum, heating on those little racks where the fruit sits, and then they have a refrigeration compressor to condense out the evaporated moisture at the back of the unit. And so they have a 24-hour production cycle, and so over that cycle the load varies, so it's quite high at the start, and then as the cycle progresses and all of the moisture is removed, that load drops off on their compressor. And so you can see pretty clearly there. So down the bottom there is a graph of a few days of their power. So looking at the blue line there, the kilowatts, you can see there there's like a bit of a lull overnight, and then when they start the cycle it ramps right up and then slowly drops down. Then they have a break when they unload, and then that repeats. So you can see there there's 1, 2, 3, 4, 5 and a bit cycles there. And so at the moment the compressor just has staging, so it has 100%, 75% or 50%. And so looking at installing VSD there will give them, and this is something they're in the process of exploring at the moment, a lot greater control over that as that load drops off, balancing the energy use with the load. And so we've done some calculations for them, and it's because it's a compressor, it's a constant torque requirement, so it's just a linear relationship with that load and power. But relative to the system they've got at the moment, it's about a 12% energy saving, or roughly about $6,000 a year, against the cost of a VSD of around about $10,000. So it would be around about between 1 and 2 year payback they'd expect for fitting a VSD to their equipment there. And that's currently what they're exploring with the equipment suppliers. Okay, so now I'll run through a work example, so similar to Forager, or this is just a bit more of a general example. Yeah, so this is looking at a fan motor. So we've got an 11 kilowatt motor, and that motor runs for about 6,000 hours a year. So that's probably 3/4 of the year the fan's running. And they have, at the moment, they have a manual dampener open. It's 80%, so it's not requiring that full load of the fan. So that's just, 1/5 shut. And so just for this example, we'll assume the cost of electricity, about 20 cents a kilowatt hour, which is very typical. So now look at this curve of input power to flow rate. So we can see that the current situations, so they've got their dampener, so that orange line. So right up in the top right corner, you can see there at 100% flow rate, it's the motor will be using 100% of the input power. And then as that flow rate decreases, so if we move from right to left along the x-axis there, that input power drops as well. But it's not quite linear, and so you can see there at zero flow rate, the fan's still using about 40% or 35% of the input power, and that's compared to the variable speed dryer, where similar at 100% flow rate, still using 100% of the input power, but as that flow rate drops, the input power drops dramatically, and a lot quicker than the dampener. So you can see there, at that 80% flow rate, which is what we're looking at for this example, the dampener, or the motor with the dampener is still using about 90% of the input power, compared to the variable speed drive on the motor, which is about 60%. And so then what does that translate to savings? So without the VSD, and then by installing the VSD on the motor, we then change to effectively the same equation, but we now have our power reduction of 60% rather than 90%. 11 kilowatts times 60% times 6,000 times 20 cents is $7,900. So you can see that that's the difference there of almost $4,000, so $3,900 per annum energy saving by installing a VSD. And for VSD of that size of about 11 kilowatts, would be roughly $4,100. So you can see there it's just a fraction over a 1 year payback period. So depending on what you consider viable for your site, that's